Surprisingly, the Laplacian derivation video got more than 10 views and 3 likes. That's unusually high participation because it's often that no one watches the video. So I'm going to get even more mathematical. I want to emphasize that this is done for my understanding. If you get lost or you don't want to watch or even give me an unlike, it's not going to be any problem for me whatsoever. Because in preparing this, I find all kinds of things that I don't understand, and then I can help fill in the gaps by going back and research and using AI and anything else I can find to try to pull the pieces together. This one's about hydrogen, finally. We're going to talk about hydrogen, which is the lead up into this. And what's our goal? Helium. Helium requires all this stuff from hydrogen. So once we get through this, we can refer back to it and we don't have to go through all the derivations again. Not surprising, I made some mistakes in the Laplacian derivation video. So because that's required for the hydrogen model, we have to go back and make some fixes, but it won't take me 10 minutes or 11 minutes. Divergence. And I'm going to use this to make sure and fix some of the things on the Laplacian. Not much, it's just like a sign, an extra sign squared that wasn't there before. But let's try to get through this fairly quickly. R squared sine theta is the correction factor for the volume. You may recall that the correction factor for the theta is R, and the correction factor for the phi is r sine. So when you multiply those two together, you get r squared sine theta. So that's the correction factor for every little change in radius, theta, and phi. And those three multiplied together, that gives you the volume, a small little volume of the sphere. Now, the divergence formula or definition says that you're going to find the change in the volume. Here's the correction factor over here, 1 over r squared sine theta, and inside here is the volume. That's the r squared sine theta, which is the volume that we're doing the change of. And you think, oh, automatically these are going to cancel out, but not necessarily. Now I've got the red line here through the sine theta and the sine theta down here because the sine theta does not vary with the radius. And because it doesn't vary with the radius, it's a constant. So I can bring that out here and get rid of one of these sine thetas. Then if I go over here to the d theta, then in this case, if that's multiplied times 1 over r squared sine theta, the r does not vary as theta varies. So that's a constant, so that one can be blown away, and that's sucked up by this r squared over here. Then finally, the partial with respect to phi, the r squared sine theta is all of the correction factor for the theta element, so that whole thing comes out. And once we get these cancellations done, we get 1 over r squared, and you can kind of follow through here. I can talk through it or you can look at it, but we get to that form, and we're going to use this form on the next page. A little bit of review, so I'm going to go through the gradient of f. Again, I'm going through this rather quickly. The gradient of a function, and it yields a vector, and the vector has 3 component unit vectors that determine the resultant of that. And here's the partial of the function with respect to r, with respect to phi, theta, and with respect to phi. And you notice here's the correction factor, 1 over r, and 1 over r sine theta. So those are the correction factors, which is mentioned up here. If you want to read through that, and you can read my cursive writing, then you're probably better than most. Here's the divergence, and this is that formula that we just went through. And what I've got here is the vector components of a general vector. I'm not saying which vector it is yet, but those various things canceled out to give us this kind of result, which I think it's rather simple to look at this, but it might be not so much for you. And then what we're going to do, in place of the a sub r, the a vector, we're going to use a vector which is the gradient of f. And that gradient of f plugs in over here. There's the d sub df over r. Here's the 1 over r df over d theta, and 1 over r sine theta df d phi. And you see those came in from this thing up here. Now, where do we go from here? Let's try to keep the momentum going. Now, another way of saying this is that it's Laplacian. So this expression and this expression are the same ways of saying the same thing. And, okay, maybe you can look through that and catch up on what I just said. So you can pause it and look at those things and see that this is the divergence of the vector. This is the divergence of a gradient, which is a vector, and those items are plugged in here. 1 over r df over dr, which matches with that thing up there. 1 over r df d theta matches up with this thing here, and 1 over r sine theta df over dq, derivative of f with respect to q, partial of course, and that matches up with this one here. If we try some simplification, these are the two expressions that are the same, and let's see, did we get any simplification here? Doesn't look like anything changed. Any simplification here? Well, I see an r squared sine down here. Where did that extra r come from? Well, that 1 over r doesn't change with theta, so I can bring that out in front, and that becomes an r squared sine theta. And the sine theta still remains inside there. And how come this one got to be r squared sine squared? That's the mistake I made before. I had r squared sine. Well, r and sine theta, this only changes with the angle. Here's the Laplacian, which we went through on that one derivation, and the one mistake that was made was this should have been r squared sine squared. Everything else was the same. Everything else was fixed, but I made a mistake on that, so you'll have to fix that in your brain. So hopefully it's not too difficult for you to unlearn this. Phi. So both of those things can be pulled out in front of the derivative, and I get r squared sine squared. That was the big thing that I needed to fix. What is a hydrogen atom? Well, it's an electron, and that electron is going around the proton, or it seems like it's orbiting because it has angular momentum as it goes around there. That has a property. Here's the Coulomb potential. Not too complicated. I think we've seen it before, but if not, here it is again. It's E squared because there's a negative E and a positive E type charge on the proton. And then here's the permittivity of free space with the 4 pi, which sets it up for spherical, and it decreases as you move away. Here's the Hamiltonian. The Hamiltonian is the energy In quantum mechanics, here's the kinetic energy term and the potential energy term. And this hat means that it's an operator because they operate on the state function, so we can crank out values. Here's the state function, and rather than just calling it psi function, we're going to say that it contains a radial part and a angular part. Here's the radial part, depends just on the radius, and here's the radial part. And we're using an R for the radial part and a Y for the angular part. Why do we use Y? That's a mystery I can't answer the question to right now. Anyway, let's look at this thing. The time-independent Schrödinger equation. Here's the kinetic energy thing. It's kind of like p squared over 2m, but instead it's got an h bar Planck's constant. Then we have variables, which is the state function upon which this Hamiltonian operates. Here's the potential energy, and it is a function of the radial part and the angular part. And then it equals E times the same state function that we have over on the left side. So the difference is, when I showed the Schrödinger equation before, we just had a simple psi function, and here we've got it broken out into the two pieces, which if we don't break it out into the two pieces, we'll never get through this thing. We'll never solve it. Okay? Here's the Laplacian up here, broken into two pieces. So we can break a product of two things. If we're taking the derivative of two things, then we can consider that the derivative of the first plus the derivative of the second. That's what allows us to do this step right here. And that's equal to, well, here's the Laplacian in two spots. Here's the radial part of the Laplacian, and here's the angular part of the Laplacian. So this thing blows up. Now, where did this come from? Well, it comes from this thing up here that we worked through. Let's see, where do we go? Okay, I just described this thing. This statement, it just justifies what I said about breaking it up into two pieces. Now, we're going to say that this L operator, and L has to do with angular momentum, because these L is used for angular momentum normally, and these angular parts are what provide the numbers for angular momentum. And we're going to say that we're going to lump all of this stuff together and put a negative h bar squared in front of it, because when we solve angular momentums, we're going to need to do that kind of thing. From the last slide, we had something that looked very similar to this. There's the L squared plugged in there, so we've got all the angular parts. This shows that the kinetic energy part of this is brought over from the last page that we just covered. See, there's that L plugged in there, which takes all the angular stuff out of there. And then here's the form of this with big brackets around the whole mess. And you'll notice that there's a Y for the angular part of the state function, an R for the radial part of the state function, and here's the potential energy. Now, what's this R times Y? Well, the R times Y is the total function, the total state function, and that's just multiplied times the potential. And that same Ry has to appear on the other side. So rather than the psi function, we've got this Ry. Now, let's see how much further. Somehow we just go to the energy. So how do we get there? Well, it's not too difficult. You divide both sides by Ry, and if we divide both sides by Ry, this is what it looks like. The R comes out, the Y goes in the denominator, the Y comes out, and the R goes in the denominator. Let's see if this next step helps any. Well, for some reason I put this potential energy in the middle, and I've got the radial part on one side, I've got the angular part on the other side. We're going for a certain solution, and that helps all that work out. Another substitution, 1 over y, angular momentum operator, times y. And if you look here, that's what shows up right there. And what we're going to do is we're going to put a lambda h bar squared. We should know that angular momentum is made up of spherical harmonics, and these spherical harmonics will give the vibration levels or the angular rotation levels of the hydrogen, and it will tell us the different energy levels, which is really where we're headed. Now, this next statement is one that really confused me, so I'm just going to talk through it and see if it works out for you. Since E is a constant, all three summed items on the left are constant, leading to the following statement. Negative h bar squared over 2m, 1 over r squared. What disappeared? Well, the r disappeared. Well, that can be lumped into a single constant. The potential value, Coulomb potential, that hasn't changed since the beginning. And then over here we get h bar squared times lambda over r squared. So you see all of this got lumped together over here into this value. And we should know this, I'm not going to prove it right now, but we should know that the values for the spherical harmonics, and in addition the energies that we come to, are L times L plus 1, where L is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, all the whole numbers. Now that's where I'm going to stop on this video, and there's going to be more to follow. We haven't actually cranked out the 13.6 electron volts. So the next one is going to lead off from here, and some of you will be real happy to skip the derivation of the Laplacian and this beginning one on the hydrogen fundamentals and go straight to finding the energy and get the heck onto helium.